last session, in session 18, we discussed alternating series, and as part of that was also absolute and conditional convergence. So I want to do a quiz now on that, and that will be next Tuesday. That's Tuesday, April 20th. That will, 21st. Tuesday, April 21st, and there will be a session 20. Okay. Now, I say absolute and conditional convergence, but be aware. You'll see that you need to know also the previous integration techniques. So it's really a little bit more than just 5.5. It's really almost everything that we have done up to now. Okay, so I'll give you two examples of what I have in mind here. So remember, let me remind you what the deal here is with absolute and conditional convergence. We have a series of the form an, let's say for 1 to infinity. And then if this series, if you ignore the signs, so you take absolute values, if this is convergent, right, then we call absolute convergence. So we will call this AC. So that's AC. What does CC mean? Means not AC. It's not in the previous case, but still convergent. So if you take the signs in, if you leave the signs, you get convergence. If you ignore the signs, you get divergence. That's what CC means. Okay, so here are two examples that I want to discuss. And you'll see here now why I am saying that it's not just about 5.5. Okay, so the first example is this one here, summation n going from 1 to infinity, minus 1, this is our series, ln n over n square. Sometimes you can guess what the answer is going to be, but often you don't, and in that case I would suggest the obvious thing to do is just always first, because we in this kind of questions, in this quiz you will always have to deal with alternating series, so that's always there, so we always have the alternating series test. So let's do that here. So the first thing I want to do is the alternating series test. Remember what that means. That means that you're going to take the limit of the general term where you again ignore the sign. So we're going to take the limit now, and we take ln of n over n squared. Of course, with limits, we're going to often have to deal with these indeterminate forms, and I hope you see that this is typically L'Hopital form. To do this really correctly, we should first go to a function, ln x over x squared. That gives me infinity over infinity, we plug infinity. So now if I do the L'Hopital, so it's actually here that I do the L'Hopital, then what I need to do is, let me write it underneath here, I take the derivative of this guy, that is 1 over x. I take the derivative of this guy, that's 2x. Now always, in this kind of situations, simplify. So what we have here, limit for x going to infinity, well, we have now 2x squared in the denominator. And if I put infinity now, that is 1 over infinity, 1 over infinity, I'll write it. So that is 0. So yes, so the alternating series test works. It means the series itself is convergent. But that's not the end of the story. Now we have to look at absolute convergence. So what that means is now we are asking, what can we say about this series? So notice now that it's the same elements here, but now it's not the limit, but it's the series. Okay, some people get confused by this, so please try to see the difference here, what we're doing. Okay, so what can we do here? Well, we don't have that many tests yet. As I said, we have seen one today, but that's not the one that we did today. I'm not going to include. Okay, so don't worry about that. Well, one of the tests that we have done is, well, comparison test, but again, I remind you, when you have these mixed forms, it really doesn't work. Okay, so the test that we did today, ratio test, would work, and if you want, you can use it, but there's another one, I'm not saying better, but there's another one that you can do, that is the integral test here. So it's a good exercise to see our integration here. Okay, so what do we need to do? We have to calculate this indefinite integral. okay? Which is, we should always try to do that always first as a limit of a definite integral. And then let's concentrate on the indefinite integral. And then later we plug it in. Let me give myself a little bit more space here. So ln x over x squared dx. We had a similar one in the previous homework problem, but you say, a substitution because ln x, that's there, and then the derivative is 1 over x. Yeah, but it's you have x squared in the denominator, not 1 over x, but 1 over x squared. So, that doesn't work well. Now here the ln is on top, and that is the case where we can start thinking about I late, integration by parts. So that's what I'm thinking about. So I late, integration by parts. Remember, this is inverse trig. That's not what the case, but logarithm, that's what we have, algebraic. Well, algebraic will be this 1 over x squared here, okay? So perhaps better now to write it as a power, a negative power then. So now we have this algebraic here, trig, this was trig, and this was exponential. Remember, this was a uv scale, so this is going to be u, this is going to be dv in our case. In other words, u is going to be the ln of x, and dv is going to be everything else, x minus 2 dx. Remember, there's a dx there. From this, we can now find out what du is by taking derivatives, 1 over x dx. And we can also find what v is by deriving, really, and that's the power rule for derivatives, so add 1 to the exponent, divide by it. Or if you want, minus 1 over x. Okay, next. The formula for integration by parts is uv minus integral v du. So if I plug this in now, I'll write it here. Continue here. Okay. U ln x v is x minus 1 over minus 1 minus. I'm just going to copy the whole thing and then we'll simplify later. Minus 1 times du was this one, 1 over x dx. Okay, so let's write this a bit nicer. The minus sign in the denominator is just on top here. We can also take care of the x minus 1 as being in the denominator. We have two minuses here, so this would be plus. And then we have, what is that now that I have in the denominator? Well, let's write everything. Perhaps, since we have to integrate, it's always better to write things in as powers, negative powers if necessary. So we have a power x minus 1, and this of course is also x minus 1, so if we combine it with x to the power negative 2. Okay, that's not hard to integrate. And then x plus by the power rule, add 1 to the exponent, divide by it, that's what we get. So if I want to write it one more time, a little bit nicer, it's this plus c, but that's not really necessary. Okay, so we can now fill this in. This is the limit for t going to infinity of the function that we had was, okay, you see it there, minus ln x over x minus 1 over x, and this is between 1 and t. So if I plug it in, limit t going to infinity, you get minus ln t over t minus 1 over t minus, and now I'll plug in 1. The ln of 1 is 0, right? This is, if I plug it in, I get 0 here, so that's 0. And then if I plug in 1 here, I get just 1. I hope you see that. Okay. Okay, so what is now the question is, of course, the limit. It's not, this part is never so important, is this limit here. If I plug infinity in this one, it's clear, this is 0. So let's already write this up, this is 0. But if I plug in infinity in this term, I get infinity over infinity. So we are again with the L'Hopital form. It's very similar to the previous one. So I'm going to do this here on the side. It's this limit that we still have to deal with. I hope you see my point here, right? There's a negative sign there, but we'll talk about that later. Oh, okay, if you want me, I'll put it there. Okay, so infinity over infinity, again, we L'Hopital. We take the derivative of the top is minus 1 over t, and the derivative of the bottom is just 1. So if I plug in infinity now, I hope it's clear that this is 0. Okay, so also this is 0. But again, this is not something you can just write down. If you don't show me this, I'm going to not give you full credit, okay? You have to show in these indeterminate forms each time. So what's the idea here? Well, everything works, so this is convergent. So this is a convergent indefinite integral, so the series is convergent. So what are we now? What does this mean? Well, if I ignore the negative sign, I get convergence, so I do get absolute convergence. And by the way, this actually means that if I would have seen this right away, I didn't need to do this. Because if this is true, then the series itself is convergent. This alternating series test only tells me that. And that's now information that I don't need anymore. I know more. I know we have absolute convergence. But sometimes you don't know this, and as I said, this is never a really big deal, so it's always safe to do that. Okay, so one more problem I want to do. So let's look at this one here. Summation n going from 1 to infinity, minus 1 to the power n cube root n squared plus 4 divided by the square root of 4n plus 9n to the 4th. Okay. Very careful with these radicals here. Don't distribute these radicals. So say, oh, okay, see in the bottom, that's all I can. No. Okay, so what should we do? Well, it's an alternating series, so let's follow just the strategy of alternating series test. Might be that we don't need it, but might be we need it, so let's do it. This means I have to calculate this limit for n going to infinity, cube root of n squared plus 4 divided by 4n plus 9 to the 4th. Okay, we have not done something like this in a while perhaps, and so let me remind you it's the same principle as if we have no radicals. We divide top and bottom by the highest degree, or perhaps better to say the dominant term. Top and bottom. Now be very careful, you will see in a while we're going to do something else. So these two things have to be really kept apart. Don't confuse them. So, okay, let's discuss what is this here. What would be the highest degree here be? The highest degree in the top would be n squared, but it's the third root of that. So what's in the bottom? In the bottom it is, don't get fooled by the fact that this is in the back here, square root of n to the 4th, which is actually n squared. So what is bigger? This is bigger. So it means I should divide everything top and bottom by n squared. You might think, oh, why don't I do L'Hopital here? You'll see. L'Hopital really doesn't work well with radicals. In fact, it makes it worse. So we have no choice. We're going to have to divide top and bottom by n squared. So by the same n squared, by this guy now, okay? So because we don't want to change anything, right? It's one of the valid operations with a fraction is divide top and bottom by the same thing. But now comes another issue. How am I going to do this division? How is this going to work? Because, let me go back to black perhaps. I'm still here a root here, and this is outside the root. Now, you cannot just go inside. You have to go inside the radical before you can do anything, but that means, of course, that you have to adjust. If you bring n squared inside a cube root, think about this. What does this become? So the whole thing, the n squared plus 4, I bring the n squared inside, is n to the 6th, right? Because think about it the other way around. The other way around is perhaps easier to see. If I take the cube root of n 6th, I get n squared. I get what I had, right? So you have to think backwards now. So this is very often the case in calculus, right? Okay, so this is that, and in the same here, we bring this n squared inside the radical, it becomes n to the 4th. And now we can carry out the division. Let's see what we have. I think I have the space here. I get the cube root. N squared divided by n to the 4th is 1 over n to the 4th plus 4 n to the 6th. And in the bottom I get square root of 4 over n cubed plus 9. Now in the top you see everything has a denominator here, so if I plug in infinity, all these things go to 0, and so will this guy. So what I'm left with is 0 over radical 9, but that doesn't matter, that's 0. What does this mean? Well, remember, in the alternating series test, this is what we want. This means convergent. So this series is convergent. So we know now that it is convergent. But that's not the answer that we seek. We want to know AC or CC. It's one of these two, but which one? Okay. What we need to do for therefore, is now look at the same series, but without the sign. So now we're going to do this without this sign. Okay? So that is 2. So now the question, is this absolute convergence? So what we look at is cube root of n squared plus 4 divided by the square root of 4n plus 9 to the 4. Okay? I copied it right? All right. This is now the limit comparison test. The limit comparison test. To see whether this converges or not. Why didn't I do this here? Because I was doing something else. It was an alternating series test, and that meant I had to take a limit. Now I'm talking about a sequence here, and this is of a form that I can use a limit comparison test. Because Bn will be now what? Remember what Bn is. You choose the dominant term in the top, so or the leading term or the highest term, whatever you call it. That was cube root of n squared. We had actually discussed this before. And in the bottom, this was the square root of n to the 4th. But unlike the previous case, right, here they are, I'm not going to simplify. So I leave them like this. Remember, that's our trick for the next step. Okay? But this, so notice that I now use not only the biggest one, which is this one, but both. The one in top is the one in top, the one in the bottom is the one in the bottom for my Bn. Okay? So, what I need to do next, so that was step 1 in this part. Step 2 was calculate this limit. And that we did in this our special way is we took the numerator of an and divided by the numerator of bn. And then did the same with the denominator. So this denominator 4n plus 9n to the 4th divided by this denominator. Okay, and that because we did it this way, we can now do the division. We see that the question about bringing things inside is now no longer an issue. It is, we can combine them. They're all third roots on the top, and in the bottom they're all square roots. So we have 4n plus 9n to the 4th over n to the 4th. And what do I get? In the top I get, let me give myself a bit more space, cube root of, these n squares cancel, but be careful, of course, there's also a second term here, 4 over n squared. And in the denominator, the n4 and the becomes an n to the 3rd in the denominator, and in the second term it becomes 9. So if I take the limit for n going to infinity, this is 1 over infinity, so 0, this is 1 over infinity, that's 0, so I get cube root of 1 over square root of 9, which is 1/3, but it doesn't really matter what it is, it matters that it is not 0 in infinity. Remember, this is now what this test, for this particular limit, this is what we need. Now, this is not the end of the story, we know this by limit comparison test. Step 3, now we're going to take a closer look here at our Bn. What is Bn? Well, it's there, right? Cube root of n squared over the square root of n to the 4th. Now I want to write this as, because what I'm thinking is a p series, so I want to write it as a single power of n, but in the denominator. So, okay, be very careful. I hope you see that this is the rational exponent that corresponds to the cube root of n squared. And here we have, well, we can simplify this now. This is just n squared, right? Okay. But everything has to be written in the denominator, n squared minus 2/3. So p is equal to 2 minus 2/3, which is 1/3. And, okay, I'm not going to make the same mistake in my previous video. This is less than 1, right? And so we, oh, no. That's not, well, I made another mistake. It's not 1. Now, see, I did make a mistake. It's 4/3. 2 minus 2/3, right? It's 6 minus 2/3. It's 4/3. And it is bigger than 1. Yeah. I have something against this thing I see. But this time I found it myself. 4/3. Okay? That means what? That means divergent. So if I ignore the signs, then this becomes divergent. So is this AC? No. What we're dealing with here is now CC. Okay, so that's the difference. All right, so again, the quiz will be next Tuesday, and please do this first before you do anything else, because you have to end before the class time finishes.